In this video, I'm going to do another Taylor remainder example. Okay, so this is example 3. In part A of this, let's find P2 of x, so the second Taylor polynomial, or second order Taylor polynomial, for f of x equals tangent inverse of x. That's centered at x equals 1. So when I say x equals 1, I mean the center point A equals 1. And then use that to approximate tangent inverse of 0.8. So before I get into actually finding the Taylor polynomials, I just want to do a brief review of what the graph of tangent inverse looks like and how we think about it. So when we talk about the original function, so thinking about y equals tangent of x has some vertical asymptotes. At pi over 2, there's a vertical asymptote. There's another vertical asymptote at negative pi over 2. And in between the vertical asymptotes, the graph looks like this. It sort of snakes up, goes through the origin, then it keeps snaking up towards this asymptote. Okay, and then it keeps repeating that shape. So the graph continues on either side of these asymptotes, and it keeps repeating that shape, and it'll have more vertical asymptotes. So even on this side, it'll still continue that shape and have another vertical asymptote here. So looking at this graph right now, tangent of x doesn't have an inverse because it's not 1-to-1. It doesn't pass the horizontal line test. What we have to do, and we've seen this before, let's put this in green actually, to make it so that it has an inverse, we have to do what's called restrict the domain. We have to restrict the domain to an interval on which it will pass the horizontal line test and therefore be 1-to-1. So the convention is to do that on the interval from negative pi over 2 to pi over 2 to make it 1-to-1. And graphically, a function is 1-to-1 if it passes the horizontal line test. So now if we take that and use it to draw the graph of tangent inverse, so let's draw some axes. We would just be looking at this part of the graph. So we're just looking at this part of the graph. I'm coloring this in blue right now. Just looking at that middle part of the graph between negative pi over 2 and positive pi over 2. And when we switch the x and the y values, because that's what we do to draw the inverse, if there are any vertical asymptotes like this, those will become horizontal asymptotes in the inverse graph. So there's going to be a horizontal asymptote at pi over 2, and also one at negative pi over 2. Horizontal asymptote there. And now drawing our graph of the inverse, it will look something like this. And that's what we get if you just swap the x and the y values. Okay, so that's just a brief bit of review there about tangent inverse. Sometimes we call this arctan of x. Okay, so if we want to find the Taylor polynomial, we got to take the function f of x equals tangent inverse of x, as well as a couple of derivatives. So we're going to have to take up to the second derivative. So the derivative of tangent inverse, recall, is 1 over 1 plus x squared. And then if we take the second derivative, we'd have to use, maybe the simplest way is if we were to think about this as being 1 plus x squared to the negative 1, and then we'd end up using chain rule on this. And if we do that, we end up with negative 2x over 1 plus x squared squared. So that's something that I'd want you to check out. Make sure you see why that is the second derivative. All right, so now that we have these, at this point, I want to leave it for you to try. Pause the video for about 2 to 3 minutes and see if you can complete the problem from here, part A. So 4, 3, 2, 1, pause the video. Pause the video and see if you can determine this Taylor polynomial and then use it to approximate tangent inverse of 0.8. Alright, so hopefully you've done that. Hopefully you've paused the video. If not, go ahead and do so now. It's really important to seize this time to get this practice. Okay, So what we do next is we need to plug in this center point, which is 1, into all of these. So I'm going to plug that into the original function, which would give me tangent inverse of 1. I'll plug it into the derivative, and this is actually easier to simplify. I'd get 1 over 2, and I have to plug it into the second derivative, and plugging it in there, I get negative 2 over 2 squared, so negative 2 over 4, which is negative 1/2. Okay, so the only thing that, out of these, the one I need to simplify is what's tangent inverse of 1. So to determine that, tangent inverse of 1, let's call it a. Let's say I don't know what it is. And if I rewrite this in terms of the original function, tangent, it'll switch the inputs and the outputs, because that's what happens when you go from an inverse to the original. So you'd have a being the input, 1 being the output. So we want to know when tangent equals 1. So we want to know when the y value of the tangent graph, whoops, let's put this in a different color, is 1. But remember, we've already restricted the domain. So we're only looking at this part of the graph, only this middle portion. We're not looking beyond these sort of middle vertical asymptotes. Like we're not looking here, for example. Okay, so when does tangent of a equal 1 in between negative pi over 2 and positive pi over 2? Well, it happens when a equals pi over 4. So that's what tangent inverse of 1 is. It's pi over 4. All right, so now we have enough information to write down our second order Taylor polynomial. So p2 of x is going to be, so our constant term is pi over 4. And then we get plus, so our next coefficient is 1/2. And we'd have 1/2 times x minus the center point, which was 1, to the first power, and then over 1 factorial. The next coefficient is negative 1/2, so we'd get minus 1/2, times, it'll be x minus the center point, which was 1. This time it's squared, over 2 factorial. And we stop there because we just want the second order Taylor polynomial. Okay, so we got our second order Taylor polynomial. Now we want to use this to approximate, well, what's tangent inverse of 0.8? Okay, so first off, the reason why when we want to approximate 0.8 into this tangent inverse function, it was helpful to use 1 as a center point, just because 0.8 is pretty close to 1. Okay, so tangent inverse of 0.8 is going to be approximated by our polynomial when we plug in 0.8. So we get pi over 4 plus 1/2 times, so 0.8 minus 1 is negative 0.2. And then 1/2 divided by 2 factorial is going to be 1/4. So I end up with negative 1/4. And then we'll get negative 0.2 squared. All right, and then plugging this into a calculator, we end up getting that this is approximately equal to 0.67540 if I round it to 5 decimal places. Okay, so we got our approximation. So we got our approximation for what tangent inverse of 0.8 is. Now, part B, let's get an upper bound for the error. So let's use the Taylor remainder formula to find an upper bound for the error in this approximation. So let's remind ourselves what the formula is. So it's the absolute value of the error is less than or equal to the absolute value of m times, and then I'll have something minus something. It'll typically be x minus a here in the parentheses. And a is the center point, which is 1. X is the number that we're plugging in to approximate what's going on there. That's 0.8. So we get 0.8, that's x, and then minus a, which is 1. The exponent is going to be n plus 1, so 2 plus 1. So our value of n is 2 here. And the denominator is also going to be n plus 1 factorial. So it'll be 2 plus 1 factorial. Okay, so we need to find m using the fact that the absolute value of the n plus first derivative, which here is going to be 3, evaluated at c, needs to be less than or equal to m for all values of c that are between a and x, that are between a and x. And a in this problem is 1, and x in this problem is 0.8 inclusive. All right, so to figure this out, I need my third derivative. So we are going to need to take the derivative one more time. So the second derivative, recall from above, was negative 2x over 1 plus x squared squared. So the third derivative, actually let me put this in a different color, the third derivative is going to be, if we were to work it out, it ends up being 6x squared minus 2 over 1 plus x squared over, sorry, to the third power. So I'm not going to go through the computation there. This is something that you can work out if you just check it, if we just go through the calculus and simplify a bit. But you use the quotient and chain rules to get this. Use the quotient and chain rules, and you'll get that this is the third derivative. So I'm skipping that computation because that's not really the heart of the problem, and I want to spend more time talking about how to estimate, how to find m, rather than how do I take a derivative. Okay, so now I need to take the absolute value of the third derivative evaluated at c. So this is going to be the absolute value of 6c squared minus 2 over 1 plus c squared being cubed absolute value. Okay, so now I need a way to find an upper bound for this and say what this is going to be less than or equal to. Okay, so what we want here is we want something larger than this fraction that we have. Larger than 6c squared. In fact, maybe let me point the arrow to that. We want something larger than this fraction, because the thing that's larger needs to go here, because this fraction needs to be less than or equal to whatever goes here. So I need a way to make this fraction, to find something that's larger than this. And it's harder in this example than the one that we looked at in the last video to just look at this and think about what value between 0.8 and 1 is going to make this as big as possible. Okay, so to do this, we can actually find an upper bound without figuring out the exact value of c that maximizes this. And that way we avoid having to do things like find the critical values, critical numbers, and then plug the critical numbers into this and plug the endpoints 0.8 and 1 into this. That's from Calculus AB or Math 11, how we find the greatest value of a function on an interval. We get to avoid having to do that, which would be nice. So what I'm going to do is two things. If I have a fraction and I want to make it larger, we want to make the numerator larger to get a bigger fraction. So what would make the numerator larger on the interval from 0.8 to 1? What's sort of the largest the numerator gets on the interval from 0.8 to 1? Well, the largest it gets is at the largest value of c. And that's just in my example, so this isn't always going to be true. I have to look at my specific function that I have here. So this happens at the largest value of c, which is 1. And again, be really careful. It's not always just largest value for the top. It has to do with the fact that 6c squared minus 2 is biggest at 1. Okay, so I'm going to replace the numerator by that. I'm going to plug 1 in for the c and get this. And now let's think about the denominator. So if I want to make my whole fraction larger, let's make the denominator smaller. And the smallest the denominator would get on the interval from 0.8 to 1 is if I make c 0.8. So this happens when c equals 0.8. That's the value on this interval from 0.8 to 1 that makes this denominator as small as possible. And plugging that in, I would get 1 plus 0.8 squared, that whole thing being cubed. And I don't need to put absolute value around this because I notice that the top and the bottom are already positive. So the general idea behind what I'm doing here is, I'm sort of, just to look at an example, think about this whole thing that I have as a fraction. Let's just say it's something like 2 over 7. And what I'm doing is, on one hand, I'm making the numerator larger. I'm replacing it by something larger, like let's say 4. And I'm replacing the denominator by something smaller than it. So let's just say 5. And when I do that, the 4 over 5, this new fraction, this ends up being the bigger fraction. This ends up being a bigger number. Okay, so when I approximate this, I end up getting 0.90684 if I round it to 5 decimal places. Okay, for something like our online homework, if we had to enter something like this in, we would want to use, unless it specifies how many decimal places, in general we should just do a bunch to make sure that we have it with enough accuracy. So now let's write down our error. The absolute value of our error is going to be less than or equal to the absolute value. We can plug in m, which is 0.90684, times, and what else is going to be there? We're going to have 0.8 minus 1 cubed, so that's negative 0.2 cubed, negative 0.2 cubed, and the denominator is 3 factorial. And if we simplify this with the calculator, we end up with 0.00121. And that's pretty low. So this is pretty good in terms of what our error is. So we've gotten an upper bound for our error here. So I'm going to end this video by just sort of making a comment about the fact that in our series here, our series, at least starting with this term, the 1 factorial term, it actually starts to alternate. We have a positive term here and then a negative one. It'll actually start to alternate here. And the comment that I want to make is, when we have an alternating series, for an alternating series, sometimes the alternating series error, so the alternating series error is better than the Taylor remainder error. So this is just something that I want you to be aware of.